So in this video, we're going to talk about how to write the dunder string method. Now, the reason I want to write the dunder string method now, so early on in the process, is we can have some data in our BST already. It's very helpful if we can actually print out the data and see what's in the tree for both visualization and debugging, right? And dunder string is actually a good method to write, because we also need to figure out how to visit all the nodes or all the data in the BST in the proper sorted order. So let's get on with it. So as before, for dunder string, we'll have a public private pair of methods, and the private version is the recursive version that takes the root node of the subtree as its parameter. So I've already have the dunder string, and basically dunder string we call a private underscore string with the root to begin with. And so this is the private recursive version. Let's take care of the base case, and we should notice now that if the subtree root is none, then what is the string we return? Well, return empty. There's nothing in this subtree, right? Okay, and then we have to build up a string from the left side and the left subtree and the right subtree. So let's have a string to begin with. And the next thing we're going to do is we're going to concatenate whatever we get from the left subtree. So that would be that would be the subtree root left child. So we'll get a string from the left subtree, and then we'll add on the node itself. So we can do string subtree root the data. So in the root, the data, we turn that into a string as well. And then finally, another recursive call to the right subtree, and that will be the right subtree. And so once we are done, we'll return this one giant string that contains first the left subtree, and then the root, and then finally the right subtree. Okay, so let me make sure I've actually gone through everything. Yeah, oh well, I did forget this. Depends on what you want, but it might be useful to insert a new line at the end. And that's that. So let's try to run this and see if it works. So if I've already written a simple binary tree test case, then insert some data and I print out the data, and let's see what we got. All right, so size 4, and even though I did not insert them in order, when I print them out after they're inserted into the tree and I iterate through the tree, they are in sorted order. So that's great. That's exactly what we want. Okay, so one thing that you kind of notice is that when we print out the what's returned by the string, it prints out the numbers all fine, all the data fine, but they are kind of in a flat structure, right? It would actually be very nice to see the structure kind of like a tree. We go down one level and go down another level. If we can actually have a little structure in our printout. So, and that's actually not hard to do. So let's get back here. So what we can do is actually just increase the amount of indentation as we go deeper and deeper down the tree. So let's actually add a depth parameter. And as I said, we will increase the indentation proportional to the depth. So I will start with a single space, and then I'll multiply that by the depth in front of the data. Okay, and every time when I recurse to the left subtree, that's going down, so I increase the depth by 1, and also when I go to the right side, I increase the depth by 1, and at the root level, I start at depth 0. So let's run that. Okay, so there we go. It looks a little better. Actually, I would like the indentation to be a little more prominent. So let me maybe multiply by 4. Okay, let's run this again. Oh, so there we go, right? So if you look at the tree, and this is our tree, 23 is at the very top, and and then it's underneath it, it's 8 and 42. 8 and 42. Now you kind of notice it's so this is the right, sorry, this is the left child, because we go down on the left subtree first, and the print order is kind of this way, right? So we print out everything on the left before we get to the root, and then everything on the right. So that's why 8 is on top, or on the left, and then 42 is on the right or at the bottom. Okay, so that's very nice. This is particularly nice if the tree gets any bigger than this, and we kind of see the structure. Okay, and now, so this almost looks like the tree that we draw on paper if you kind of tilt your head to the left 90 degrees, right? So kind of you rotate this tree 90 degrees counterclockwise, except it's kind of flipped upside down, right? So this is what I would like you to do. Can you actually modify the underscore string so that we don't have to do the flipping, right? So if we can print it out this way, then you look at this tree here, you tilt your head counterclockwise 90 degrees, it really looks exactly like that. So can you make the output look like that? And yes, it's hopefully you figured that out. It's fairly simple. You really just kind of switch the order. Instead of printing the left subtree first, you print the right subtree and then the left subtree. And when you do that, when you do that, and you run it, and here, now this tree looks very, very close to this tree that you draw on the paper. So we've done the string, and done the string, we traverse the entire BST in a sorted order. Right? We visit the left subtree first, and then the root, and then the right subtree. So that's really, in most cases, how you would traverse a BST, because it's sorted, right? And this order, left subtree, root, and then right subtree, this order actually has a name. It's called in-order traversal. There are other type of traversal, such as pre-order and post-order, depending on what you visit first. We might talk about those later. And now, one thing I want to point out is, so dunder string is really good for us, for the humans to see, but it's not very useful for automated tests, because if you actually look at my test string here, I really don't have an assert. So even if this BST, the dunder string, even if it returns nothing or something completely wacky, this test, if I don't look at the result, I don't really know. Now I could, perhaps make this string an expected string, and then I make sure whatever that the string returns, the string matched this string here. But that is very kind of fragile testing, I would say, because even if you have an extra space here, there, like if you put, instead of 4 there, you put a 3 or something, all of a sudden your test will fail, even though, then the string still works correctly. So then the string is never good for automated test, and will to really write automated tests to make sure what's in the tree are the correct data. We really need an easy way to get all the data from the tree rather than a string representation of all the data from the tree. So that would be our next topic.